Hello guys, welcome back to my channel. So in this video, probably the first ever time on YouTube, I'm going to do a thorough derivation of the odd part of Kummer's log gamma expansion. So with that being said, I hope you watched the previous video where I did the even part, which still required a significant amount of work. This video it might be pretty long, so just heads up. Let's get started. Okay, so the integral we have to calculate is basically going to be this. Yeah, let me just fix a little. Okay, it's going to be 2 times integral from 0 to 1 of the natural log of gamma of x times the sine of 2 pi n x dx. This is the Fourier series on the closed interval 0 to 1, and this 2 is just a sort of a normalization factor. What we really care about is this, the factor that's ahead of the 2, the I. I'm going to call this the I integral, the main integral. So for doing this, you might say, why can't we just use symmetry like we did before? Well, if you try to do that, both the parts are sort of going to like cancel out, and like you won't really get anything fruitful out of it. So what do we do in such situations? Well, you can't really, you're kind of running out of options. Sine is fine, you can handle it, it's in the numerator, there's certain degrees of freedom. But the natural log of gamma, well, that's a really non-trivial function, and that requires work, and it requires you to notice the series expansion of the natural log of gamma. You can take the product formula for the gamma function and take like a natural log of it, so that the product becomes a sum by the properties of the natural log, and you basically get minus Euler-Mascheroni times x minus natural log of x plus the infinite sum running from k equals 1 to infinity of x over k minus natural log of 1 plus x over k. What you notice here right now is that there's this linear terms, one that's outside and one that's inside the summation, and same thing with the natural log going on, with the exception of different arguments. But so what I'm gonna do is I'm gonna take I prime, what I take all of these linear terms and basically do the sine, because what we have to do, we have to multiply each of these individual parts with a sine and integrate them out. So for I prime, I'm just doing the linear terms. So this and that, I'm of course going to retain the infinite sum multiplied by a sine and integrate it out. So that's just the linear part, and I'm going to call the integral I prime. In the end, I'm going to have to do I prime and then work with the logs separately. That will be I double prime, and then I add things up, I will get I again. So that's the way I'm going to do this. So with I prime, we have minus Euler-Mascheroni, integral from 0 to 1. This is the first term outside the sum. So x times the sine of 2 pi n x dx plus, I'm going to pull the sum outside shamelessly and then integrate from 0 to 1, x times the sine of 2 pi n x dx. For the first guy, it's again simple integration by parts, nothing too fancy here. So we integrate out the sine to get a negative cosine. That wipes out the negative up front. Divided by 2 pi n. Don't forget to reverse the chain rule as well. From 0 to 1. Minus Euler-Mascheroni over 2n pi. Integral from 0 to 1. Just cosine of 2 pi nx dx, and I'm gonna have like a similar sort of thing going on, except I'll have a negative because there was no negative to cancel that out. So sum outside, I believe I have 1 over 2 pi n k, and then again cosine of 2 pi n x times x from 0 to 1 minus integral from 0 to 1 of cosine of 2 pi n x dx. Now I just want you to notice what happens to this cosine integral. Integral of cosine is sine divided by 2 pi n. Sine evaluated at 1, so sine of 2 pi n will be 0, right? Sine of any integer multiple of pi is 0, and sine of 0 is also 0. So this entire thing will go to 0. So will this bottom integral. And so this simplifies a lot to just give us Euler-Mascheroni. I don't know why my series is getting so excited about. I guess it likes Fourier series. So to give us, well, cosine of 1 is 1, x at 1 is 1. So we have Euler-Mascheroni over 2 pi n. X at 0 will make the entire thing 0. And same thing here. Sum from k equals 1 to infinity of 1 over 2 pi n k. This looks like a harmonic series, but don't worry about it. We're not going to actually diverge. This was just a fragment of the entire thing. I'm probably doing it in a more shabby way than what other sources might give you, because they might want to like club the divergent terms together and then work with them. I'm just gonna keep this. Not gonna change the form. I'm just gonna keep it, and like this is a less elegant but still an effective method because infinities will cancel out. That's how regularization works. Okay, now we've done I prime. I guess we should work with I double prime now. Let me define what that is. So I'm gonna do this natural log first because it's a lot easier. The argument of this guy is complicated, so I'm just gonna do for I double prime this negative natural log of x with the sign integrated. So I will have negative integral from 0 to 1 natural log of x sine of 2 pi n x integrated dx. Now again, I think the approach that we sort of mutually agreed on is integration by parts. Again, integrate this trigonometric term and then minus 1 over 2 pi n integral from something actually 0 to 1 of this cosine of 2 pi n x over x dx. Well, but this diverges, doesn't it? Like for 0, if you remember the cosine integral function, it diverged at 0. So the best way to be a little consistent or a little more careful is by taking a limit here and changing this to epsilon. I should have done that here for the harmonic series, but I think it's like implied. Here it's more like we have to like define it explicitly because we're gonna have to use this epsilon later. Here it's fine. I can like make that like limit come in later on when I'm actually implementing or working or trying to cancel the infinities off. Okay, I hope that the argument convinces you. The first term, natural log of 1, will make the entire thing go to 0. For 0, natural log of 0 diverges, cosine is 1, so we have to be careful. Again, take the limit as epsilon goes to 0 of natural log of epsilon over 2 pi n. And I would like to do a z substitution here, 2n pi x. So with that substitution in place, I have limit as epsilon goes to 0 divided by 2 pi n integral from 2 pi n epsilon to 2 pi n of cosine of z over z dz. And now it's actually time to do a quick aside. because this is kind of looks like a form we've been working on in a previous video on cosine integral functions. Because remember, a cosine integral function, and this is a side with a green star, of z was negative integral from z to infinity of cosine of t over t dt. Notice we have like the same integrand going around, but what we can do is sort of work with these upper and lower bounds. So we have now 2 pi n epsilon to 2 pi n cosine t over t dt. We can break them up. Negative integral from 2 pi n to infinity of cosine of t over t dt plus 2 pi n epsilon to infinity cosine t over t dt. Again, I'm assuming that 2 pi n epsilon is smaller than 2 pi n, and of course if epsilon is like small going to 0, that will be the case. But notice what this is. This is just the cosine integral of 2 pi n minus the cosine integral function of 2 pi n epsilon, which I can represent as cosine integral of 2 pi n x evaluated from, let's see, epsilon to 1. I can do this. I can do this simplification, and this is what we have up here. So it's time to get back to our original color of doing these things. And notice that I double prime now simply becomes just this factor of 1 over 2 pi n natural log of epsilon minus, I believe, limit as epsilon goes to 0 of ci 2 pi n x evaluated from epsilon to 1. Okay, this is I double prime. Time to combine these things. Time to combine I double prime and I prime. So if I just do that, I prime and I double prime, notice what's going to happen. So we're going to have this, and then of course this maybe now it's time to take a limit as, I don't know, capital K goes to infinity, 1 over 2 pi n k minus, well, you have that diverging natural log term, minus basically the cosine integral term. So that's ci 2 pi n x epsilon to 1. Okay, now notice what's going to happen, and this is like a clever observation, and the power of regularization. Notice we have this. I just pulled out the constant, so sum from k equals 1 to capital K. I'm also taking the limit outside, capital K, 1 over k. Since we pulled a minus out, shouldn't this be like a plus in here? But no, I'm switching. So notice that like natural log of 1 over epsilon will introduce like another negative sign, but the limit will now have to be flipped to an infinity. So if you say limit epsilon goes to 0 natural log of epsilon, you can write this as negative natural log of epsilon goes to 0 of natural log of 1 over epsilon. But then you can, 1 over epsilon becomes infinity, so you can just change the limit to this, and that's exactly what I'm doing here. I should just like cordon this off there. Yeah, natural log of capital K in this case, and the limit as k goes to infinity is outside, minus, well, let's see what we have. We have ci of 2 pi n plus limit as epsilon goes to 0 Ci of 2 pi n epsilon going out. Notice what this is. This is the harmonic series minus natural log of k, as you have infinite harmonic term and infinite logarithm. So that just by definition, the Euler-Mascheroni constant. So you have another Euler-Mascheroni constant here, and the cosine integral terms are as it is, because we aren't really doing anything with them now. Notice this epsilon term is going to diverge, but again, I'm going to account for that later. Notice, see, although we had a divergence with the harmonic series and the natural log, it nicely sort of cancelled out to become a convergent Euler-Mascheroni constant. So I prime plus I double prime is just the difference of these cosine integral terms. I think I forgot to like have a factor associated with them, I think, because let's see, if when I write this out, I had a 2 pi factor outside, so I think I forgot that like throughout. That's unlike me, but at least I realized that. So again, I'm gonna have that just come in here, 2 pi n epsilon over 2 pi n, and that's it. This is the end of part 1. Part 2 on a fresh page. See you there. Hope don't die, please. So, well, we accounted for this term, that term, and the inside linear term. Now all we have to account for is this natural log of 1 plus x over k inside the sum term. So how are we gonna do that? Well, slow and steady wins the race. Just write it out. There's no way out of this. So take the sum outside, and we're gonna have a negative coming out. Integral from 0 to 1, natural log of 1 plus x over k, the sine function of 2 pi n x dx. Okay, now again, integration by parts is the name of the mantra today. Sum from k equals 1 to infinity. Notice the ubiquitous cosines over 2 pi n. Natural log is untouched for now. From 0 to 1 minus, I believe, 1 over 2 pi n k. I'm just skipping some steps. You can see by differentiating. Pause the video if you want, like, differentiate the natural log of 1 plus x over k and obtain the prefactors. 1 plus x over k dx. There we go. That's it. And now what I'm gonna do is I'm gonna call this entire thing along with the negative sign, actually, I sub k, such that I triple prime just becomes this, whatever this is. So cosine at 1 will be cosine at 2 pi n, so that's 1. Cosine of 0, well, is also like 1, but this thing here, it will be natural log of 1, so at 0 it goes to 0. So we just have whatever happened at 1. So I believe natural log of 1 plus 1 over k over 2 pi n, and I said we're calling the other thing I sub k, so let just that be that. Now I sub k is sort of like without the sum, so I sub k must be summed. Okay, now it's time to do I sub k. Maybe I should choose a better color. Let's see. Yes, okay, white is fine. So I sub k is negative 1 over 2 pi n k integral 0 to 1 cosine 2 pi n x divided by 1 plus x per k dx. You can do a quick substitution. notice you have 1 over 2 pi n. We can sort of use the k in the denominator actually. So this is going to be from k now to k plus 1 according to our substitution. Again, pause the video, go ahead if you don't believe with me. 2 pi n z minus, I believe, 2 pi n k over, I believe, z. X plus k is z, so that you get a z dz. Okay, 2 pi n k, k is an integer, right, because that was the summation index. You use the property of the cosine, you just get 2 pi n z. So we have negative integral from k to k plus 1 cosine of 2 pi n z over 2 pi n z dz. We can do another sort of substitution where u equals 2 pi n z, and notice what happens here now. Negative 1 over 2 pi n integral 2 pi n k to 2 pi n k plus 1 cosine of u over u du. And again, we went through this on the previous page. This is the difference of cosine integrals evaluated at each of those upper and lower bounds minus cosine integral 2 pi n k and now it's time to sum. So when you do this Royal sum from k equals 1 to infinity, you notice that the inside part is sort of going to telescope. So let me just write that. I talk faster than I write clearly. So if we can just like write some terms down to see the telescoping nature of this infinite sum, we're going to have cosine integral 2 pi n times 2 cosine integral 2 pi n times 1 plus cosine integral 2 pi n times 3 minus cosine integral 2 pi n times 2. That goes on until you reach like the last term, for which you need to do a wholesome sort of substitution. 2 pi n I believe k plus 1 minus cosine integral 2 pi n k, and these are all at k equals infinity. Okay, notice the pattern here. This cancels out with that, which means this will cancel out with the next term. I think this will cancel out the previous term because there's nothing to up front to cancel k plus 1 with. So what we're left with is simply cosine integral of 2 pi n over 2 pi n, that was this first term that did not cancel, plus limit as k goes to infinity cosine integral 2 pi n k plus 1 over 2 pi n. Notice what the cosine integral was like. It was ci of z was the negative dt, right? So if you take like infinity for the lower bound, there's like not much area left to like integrate over. So it's infinity and infinity. So you can sort of estimate that this is going to go arbitrarily small, just because of the definition or the way you define these things. Like you could have taken limit as some like z naught goes to infinity out, and then notice that like the lower z goes to z naught. You notice this. You can do some real analysis if you're really rigorous into that. And this will actually become arbitrarily small. Like you can argue with a Riemann pavings argument or dyadic pavings or whatever, measure zero argument. So this is what I sub k summed over becomes. So now it's time to sort of replug this back into our I triple prime. So with the right choice of color that we had initially, I'm going ahead and plugging it back. But notice this natural log, you can write it in a really creative way. Sum from k equals 1 to infinity. You can write this natural log as k plus 1, natural log of k plus 1 minus natural log of k, and of course the I sub k term that we summed over, and we're going to plug that in later. So notice again the telescoping series for the natural log. So natural log of 2 minus natural log of 1 plus natural log of 3 minus natural log of 2 goes on till the infinity case, and this is the healthy way of handling these things. K plus 1 minus natural log of k, and of course then there's like the summed I sub k term. So notice this cancels out with that. K cancels out with something behind it. This is 0 anyways. This cancels out with something up front. So we're just left with 1 over 2 pi n, limit as k goes to infinity, natural log of k plus 1. And I believe plus cosine integral 2 pi n over 2 pi n. And now I think it's time to sort of revert back to our I, because I is now going to be I prime plus I double prime plus I triple prime. So yep, let's do that on a fresh page for the conclusion. So I'm just going to write the terms down so that like people don't think I do a big jump here. So I is going to be negative cosine integral 2n pi over 2n pi, limit as epsilon goes to 0, cosine integral 2n pi epsilon over 2n pi, plus limit as k goes to infinity, natural log of k plus 1 2 pi n plus ci 2 pi n over 2 pi n. Notice this cancelled off nicely, really nicely. Now how do we estimate this cosine integral at evaluate at 0? For that we need to use from one of my previous videos the formula that I derived for the cosine integrals, Euler-Mascheroni plus natural log of z. Everything on this channel is for purpose, and I derived this just before this video so that people don't feel like I'm just waving my hands here. Z to the 2k over 2k times 2k factorial. Check that video out if you haven't. So Ci of 2 pi n epsilon is gamma plus natural log of 2 pi n epsilon, sum from k equals 1 to infinity minus 1 to the k, 2 pi n epsilon to the 2k factorial. So notice that like if we take the limit as epsilon goes to 0 on both sides, then we have to like take a limit with the natural log, but epsilon raised to higher and higher powers that are 1 and greater, or rather in this case 2 and greater multiples of 2, this will become smaller, will become a complexity that's way smaller, and we can ignore that. And that's what the limit does, right? It does an approximation, and that approximation we can ignore because epsilon is getting really small when we raise to higher powers. So this is just going to be limit as epsilon goes to 0 of natural log of 2 pi n epsilon plus a free Euler-Mascheroni constant. I like how, this stuff is like just free, it's like floating around there. But now this just means that like our I is simply, instead of this we can just substitute this now. So plus natural log, I could split this up with log properties, divided by 2 pi n because that was the prefactor up front, plus limit as epsilon goes to 0, that's the epsilon part of this, natural log of epsilon over 2 pi n, plus limit as k goes to infinity, natural log of k plus 1 over 2 pi n. Do like a change of limits. So notice this will be negative natural log of 1 over k plus 1 2 pi n, k going to infinity. K goes to infinity, the inside goes to 0, so we can just do a change of limits here from k to epsilon, and you can replace entire k plus 1 in epsilon. So we have this, the prefactor, or at least like the finite terms I'm just putting out there, limit as epsilon goes to 0. We can sort of take a common limit now, right, according just to that. And this sort of annihilates each other, regularization if you want to call that. And at the end we're just left with this for I. But notice what like Bn was, the coefficient actually was, it was 2i. So divided by 2, we just get this. And that, boys and girls, is the final answer we are actually looking for. If you don't believe me, just do this integral yourself. Yeah, just like take a piece of paper, pause the video, do this integral yourself. If you don't believe me, you should get the same answer. This result is pretty satisfying in the fact that Euler-Mascheroni constant just like pops in. Now, one viewer requested me to sort of do, so remember what our Fourier series actually looked like, right? We had a cosine term coming up. So we had 1 over 2n cosine of 2 pi n x. This was the an term. We're summing here. Plus, and now this is the bn term. Plus, I think there was like a prefactor up front. Oh, sorry, there was a 1/2 natural log of 2 pi from the regular integral from 0 to 1. All of this was just equal to natural log of gamma of x on that interval, right? So someone in the comments just requested that like I write this in terms of only sines, so I'm gonna just do that here. So the only thing that's like not a sine or whatever is this cosine. So cosine from n equals 1 to infinity, 1 over 2n cosine of 2 pi n x. Surprisingly, a simplification does exist. You can use Euler's formula here. 2 pi I n x e to negative 2 pi I n x. And I took the 2 outside, that became a 4. And of course we're being summing from n equals 1 to infinity. So I can take a negative 1 over 4 out because I'm going to look at this as e to the 2 pi I x raised like times n. So that's like e to the 2 pi I x raised to the n. And I'm going to use the natural log Taylor series to get absolute value of 1 minus e to the, that's why I'm taking a minus, because we have alternating terms. If you take a minus, one of the alternating terms sort of, it becomes even, but you also have this spare minus 1 coming out. Just like, okay, there's too much words. Let me just briefly like talk about what I'm saying here. This is this Taylor series expansion of so if I take a negative x, I'm gonna have negative x to the n, so that will cancel out with this n, but I'll have still a negative 1 to the 1. So that will come out. That's why I'm taking that negative out here. Going 2 pi I x. Similarly for the other term. Again, pause the video if you don't believe me, but this is the standard. You should kind of be used to this now. I'm gonna call this S. So S is now negative 1 over 4. I can do some juggling inside. Again, it's an absolute value, e to the negative I pi n x. E to the I pi. Wait, there shouldn't be an n, because that sort of goes away in the natural log definition. Just x. E to the I pi x. Natural log e to the I pi x negative I pi x e to the I pi. There should be a negative here and no negative there. Pause the video if you want. I'm just gonna like go fast. The video is a little long today. And now sort of use like the log property to separate these things out. So you have I pi x minus I pi x from here, plus 2 times natural log e to the I pi x minus e to the negative I pi x. Goes away. Minus 1/4. 2 times natural log of 2 plus, I believe we are gonna also have to take natural log of I into consideration, because we're going to be dividing by 2i, so we need to multiply by them. So because natural log of e to the I pi x minus e to the negative I pi x over 2i. Notice the argument for the third natural log is simply going to be the sine of pi x. This is just I pi over 2. 2 times natural log of sine of pi x. But see, the thing is, we don't really care about this imaginary stuff. We don't really care about what's imaginary and like what's not. We just want everything real because this was real to start with. So I think it's like best to sort of ignore this. It's just an additional phase factor in the complex plane that we don't really need to worry about. It's there for some theoretical, more formal reasons. Minus 1 over 4, and we can sort of club this up to be natural log 2 times natural log of 2 sine of pi x negative 1/2 natural log of 2 sine of pi x. But like, notice what we had before. In the entire thing, this will just be replaced by this factor. So, and we don't even need to like sum on that anymore, so because we evaluated that sum right when we were doing the sine. Of course, there exists literature where you massage the terms even more, but I don't think I am a good massager. I believe I gave you a good reason why things are, and I believe this was probably one of the cleanest explanations, at least the ones I found, and the ones I actually worked on myself. So I think we should be grateful I found this. one of the first times I'm gonna find this on YouTube, I guess. So yes, I think there we go. I think this should satisfy you. Everything is in terms of a sine or a constant. And yep, there we go. See you next time. Stay tuned for more. Thanks for watching this video, guys. Like and subscribe. We're growing and I want to grow more so that I reach more people. Stay tuned for more content. Peace out.